All right, so I got the signal from the boss, so I'll get going. I'm Bob Harper, and what I want to talk about these lectures this week is I want to present type theory from a computational perspective. That's a sort of theme that I'm doing, and it's based on the premise, which I conceive of as the fundamental premise of constructivism, which is the idea that a sufficiently expressive programming language is a foundation for all of mathematics. So that's the idea that I want to pursue this week, and the origins of this idea. So the perspective is I want to look at type theory as if it were a programming language, and I'm emphasizing that because something has been, in my mind, getting lost in the accounts of type theory, in which the connections to computation seem to be possibly not as well appreciated as they might be, so I'm going to do this. And so the reference point for this, the main reference, is a much misunderstood paper that people cite, and I bet they never read, called Constructive Mathematics and Computer Programming, a very landmark paper, monumental work. And I'm going to be using that as a foundation. And so on computer programming, and also by Constable, I will say, et al., okay, which is the new Perl proof development. I'll just say the new Perl system in semantics, although I will be looking at that. You can get these things from, if you look at newperl.org, there's lots of stuff there. So we can look there. So these are my principal kind of reference points. And my plan for lectures this week is that I want to develop type theory starting with computation. Because the idea for me, the idea that I'm pursuing here is an issue about what is constructivism. I'll come back to that a little bit later. So I want to do this. And in the process, and what I'm going to do is this is going to be, and what's important is, this is going to be a theory of truth. Okay, that's what is very important in the development that the perspective I'm taking. I'm going to be talking about what is true. And you might ask, well, what do you mean by a theory of truth? And my belief, my feeling is, the only satisfactory theory of truth that I know about is one that's based on computation, and that's what I'm going to develop. And I want to contrast this thing with what is the thing that people start to think is type theory, and I don't. I want to sort of think of this as, contrast that with formalisms, okay, which provide us with something much less than a theory of truth. They provide us with a theory of proof, but by proof, the term here is confusing, so maybe I might use the word formal proof, emphasizing formal proof or derivation, because because I want to contrast that because it's a theory of truth that's based on, and people get confused about this because people are a little bit confused about, I think, about what is the meaning of the propositions as types principle and why something that goes down as the Curry-Howard isomorphism is irrelevant. I will get to that, okay? So that's one of my provocative claims that I'm going to hopefully intrigue you with, that I'll talk about this week. So this is what I'm going to do, is I want to present a contrast between semantics and syntax, and everyone is kind of stressing the syntax and losing track of the semantics. And so that's the main thing that I want to do. The other thing that I want to do is I want to bring you, at least at the level, I hope to bring you up to date on the most recent developments in type theory and what is called cubical type theory. Maybe you've heard about this, or higher dimensional type theory. I want to explain a little bit about this, about higher dimensional type theory by the end of the week. And I will be doing it from the computational perspective, that it's all about writing code. Okay, so that's what I'm going to do, and I hope I can pull it off. It's a matter of how much time and how clever maybe I am or not, and maybe I'm not, and being able to explain some of these ideas to you. So we'll see. So that's my plan. So when I say that a sufficiently expressive programming language is the foundation for all of mathematics, I mean we're going to start with the notion of computation, and we're going to build up to many things that are by now well known, and some things that have only been developed in the last few years, which involve this higher dimensional structure in connection with algebraic topology and other branches of math that previously seemed like completely out of the realm as far as what we were doing in type theory is now completely being incorporated really in that setting. So that's what I hope to do. So that's my plan. And in the process, I hope to play on these contrasts here between the semantics and the syntax and downplay the role of formalisms. Okay, so that's the overall plan. And so let's, I think the only thing to do is to get started. Okay, so the way I'm going to go about this, here's what I want to warn you about. I'm sure that a good percentage of you think you already know a lot about type theory. You are the ones who are in danger here because you're going to jump to conclusions that are not valid. Okay, and at least according to me, according to my lectures. So the people who are naive, who haven't had anything before, you're in good shape. Okay, it's the people with prejudices about what's true about type theory, and they know everything about type theory. Baloney. Just because you can play the video game with cock doesn't mean you understand type theory. No. Okay. No. All right. So that's very important. Okay. So you beginners, it's going to be good for you. Okay. So what we do is the thing that is a little weird here. In particular, I'm going to show you some things that are theorems. I mean, it's a little grand to call them theorems, but there are facts that I have to show you are true, which are not true by definition. They're true by reasoning. Okay, so I'll show you how that goes in a minute. Okay, so the biggest idea is you start with a programming language. I don't know whether any of you, if you've studied a bit formal type theory, I've even lectured about it. You start with a programming. What happens in formal type theory, you write down a whole bunch of rules, and allegedly people wave their hands and shout vigorously about, Curry Howard and words like that to somehow convince you that it has something to do with programming, except that a lot of times the story is lacking, and in fact, a lot of times the story is just wrong. So a subtext of what I'm going to say is a misadventure in type theory that involved writing down a formalism that was allegedly a kind of constructive type theory that has no computational content. I don't think it can be given computational content, which is a formalism called homotopy type theory. And I don't consider that to be, I consider that to be deficient from a computational point of view. I think it's irreparable. Okay, so I'll give you an example that everything I'm saying is not just like a matter of some kind of doctrine, it's a matter of actual experience in the last few years of things going wrong. So it's not automatically the case if you write down a bunch of things with horizontal lines and stuff that you're defining a programming language. No. Okay, so I want to explain a little bit about that. Okay, so here it's going to be unambiguous. Okay, the main idea is I start with a programming language. And what that means is, in the present state of development, I would like to relax this someday. I don't have any ideas or anything to say about that at the moment, but we'll start with a deterministic operational semantics or transition system. Okay, which is given by basically two forms of judgment. So I will assume that we have available to us, and I'm not going to belabor this. I don't have time to develop everything from scratch. So I'm going to assume some working knowledge, some idea of what is often called higher order abstract syntax. Okay, but abstract syntax with binding and scope. All right, I'm going to assume you know about this because I can't lecture about that and hope to get anywhere, okay? So in particular, the notion of substitution for variables. If you're not familiar, if you are really a beginner, then we're going to have to deal with this offline. Okay, so the notion of substitution for variables is very important. Because a critical thing in all of this is that we have a proper mathematical notion of variable and not the thing that in programming languages are often misnamed variables. So we want to make sure that we're just dealing with what you learned in elementary school and not what people kind of distorted that into later in your life. Okay, so this is what we're doing. So I'm going to assume I have that. So it means I have forms of expression, and I'm going to with binding and scope. So that's where I'm assuming you know what's going on. And if I want to be completely generic about it, I'll just use the letter E, but sometimes I'll use letters that are more suggestive of their role. Okay, so we have forms of expression E. And then we have two what are called judgment forms, and you've heard that terminology maybe. And I think this is also confused, but anyway, I'll get to that later. So what we have is the idea of when is something of value, when is E fully evaluated. So I'll just say the assertion states that this means that E is fully evaluated. That is, there's nothing left to do. And I'm going to give an example. Example of this is I'm going to have the booleans, and I'm going to stipulate that true and false, which I'll write like that, are values. Okay, there's nothing more to say about those. So we have the notion of E as a value. And we have the notion of transition, okay, which is, means one step of simplification. Of E according to a deterministic rule, okay, which I will specify when I define particular transition systems. I'll be specifying something that is going to turn out to be deterministic in every case. It would be nice to extend it to account for non-determinism. There's lots of reasons to want to do that. It's not in scope at the moment. There are technical reasons there are technical challenges there to make that work. Okay, so these are an important thing. And then sometimes we have a derived notion that we use. Oh, I'll write it like that. E evaluates to, and now a lot of times I'll use a letter like E naught, or sometimes I'll use a letter like V to remind you that the right-hand side is supposed to be a value. So what this means is E transitions in 0 or more steps to something which is a value. Okay, so that's the idea. Okay, so that's and so what's a little example of that to get me started? Surprisingly enough, I will be able to say interesting things about the booleans. So, all right, so what I will do is I will look at the conditional. So let's say we have if, and I will call this, in my notes I call it N and P and M. I write things in curried and uncurried syntax according to my whim. I sort of want to associate the then and the else clause, okay, with the if, and then think of this as the principal argument put it last. That's just, it sort of regularizes things in a way, and I kind of like to do that. So this is a form of expression. So really, if I don't want to prejudice it with letters that seem suggestive, let's just call that E1, E2, and E. Now, in fact, I'm going to end up using certain letters, but I'll show you what's going on. So all I do is I just write down an operational semantics for this. So what I do is I'm going to say the transition is inductively defined to include at least these rules. Okay, so I will have this transition. I want it to have at least these rules. I don't even care about the inductive definition so much. Well, I do a little bit. Let me just say these are the rules that govern the if. Oops, sorry. That should say E prime. If E transitions to E prime. And I guess I'm going to assume you know how to read inference rules and what are inductive definitions. That's another thing that it's not possible for me to lecture on right now, but maybe in the first week you got a taste of that. So that would be good. Okay, so we have this kind of thing. I know it's going to look familiar to you, but I'm sort of inviting you to just pay attention. So things get weird right away. Okay, so let's see. So we'll have a rule like this, and then we know how to branch according to whether something is true or false. So I do that, and if you don't mind me abbreviating two rules, I have two different rules here with two different conclusions, blah, 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 and then that would go to E2, and then I'm done with my specification. Okay, so I've got a tiny little programming language here, which you could call, if you wanted to be fancy about it, you could call these binary decision diagrams. Okay, and I will say something about binary decision diagrams in a moment because it pertains to something called the Shannon expansion, which is actually just a universal property of the Boolean. So we'll get to that in a minute. Okay, so that's the thing we're writing down as our starting point. Okay, now the next thing we do is that is once we have defined what a programming language is, we work on the following principle, which I think is very important. Types as or types are, I will be sort of declarative here. Types are specifications of program behavior. Okay, this is the thing I want to start with. Okay, they're not, so to say, pieces of syntax. So that is what I am, one of the ways in which I'm deviating right away from very peculiar things. So I'm going to develop these ideas incrementally. So let me just start with the first increment, okay? So I'm going to define, so this is the idea. So if I go informally, okay, I'll say little thing, I'm going to show why this ought to be the case, but I will explain to you. I will be able to say something like this. Well, actually, prior to that, I should be able to say, so, okay, let me write it down here. I'm going to have two principal forms of judgment, and I'm going to actually have to, what are called forms of judgment. And the interesting thing is this use of the word judgment is present in Martin Luft's 1978 paper, Constructive Math and Computer Programming, and it's been abused to death, okay, by absolutely everyone ever since then. So what this is that these are expressions of knowledge. They are expressing that I know something. Now, I also don't have time to go into it here, but this already begins to touch on a theory of truth that Martin Luft developed based on Brouwer's ideas, which is based on the premise, if you don't mind me saying so, is based on the premise that mathematics is a human activity and it's all about communicating between people. And how do we communicate between people? Obviously by speaking, we have forms of expression. And how do we communicate facts about infinitely large, so to speak, about infinities in a finite way? If we're talking about people, we have to talk about it in a finite way. The way you do that is with an algorithm. That's the entire point, okay? That there's no way for me to convey to you infinitely many utterly disconnected facts about the natural numbers other than by having some kind of uniformity which is expressed as an algorithm. That's the basic premise. Okay, so I can't say any more about that, but the point is that it's all about what you and I know, and you telling me what you know, and I tell you what I know, and we agree what's going on, and we agree because of the fundamental faculties given to us by evolution that we understand the notion of computation by virtue of being born. Okay, so that's the premise. Everyone understands the idea of an algorithm. Okay, that's the beautiful thing. I like that very much. You don't have to believe me, but anyway, it's the premise of how this all works. Okay, so the two principal forms is saying that I know that something is a type. Now I'll start using letters that are suggestive. This is any form of expression. And now that, well, let me just say this. We'll say A is a type. I don't need to spell that out. And I will say M obeys the specification given by A, or M is a program that when you run behaves the way A says it runs. Now here's the first thing to notice, okay? So these are these are behavioral, and I'll say on this board what I mean to emphasize this. They're not structural. Okay, and second of all, both M and A, I'll just use the letters in this here, are programs. There is no a priori distinction between something being a type, something being an element, about what are the elements, what are the types, what are the no, okay? Completely not the case. So let me give you some examples. So you will believe me. I'm going to actually define some of these things in a moment, but I think you will believe me with like maybe the first thing I'm going to write. I can say something along, well, first of all, I can say something like this. I can say, well, even before that, I can say, well, bool is a type. So that's just a fact, okay? That's what I'm going to do. Now, when I do this, I'm assuming that I have available I forgot to write another form of expression that I have up here, which is bool is a particular value. I forgot to mention that, so I'll throw that in. Okay, so that's a particular value. And I'm going to claim that this is a type. And then I'm going to claim things like the following. That true is actually an element of bool. That will shock you. That false is going to be an element of bool. This will turn out to be, although what I'm writing down it will be true by definition that this is the case, but what I'm writing down is not the definition. I'm writing down some observations about a thing I'll define in a minute. Okay, so now it becomes more interesting things. For example, and I noticed the way this works, so I'm going to say, well, if you have any boolean at all, and maybe you have, I think I used, let's call it M1 and M2, I'm going to be able to prove something like this A, where A is some type that I write down, then you could easily imagine that the conditional, everything now is just me waving my hands, but I will try to show you, will be of type A. This is kind of familiar. This is kind of familiar. Okay, so this will turn out to be a fact, not a definition. And in fact, it's not even going to be as general. I can state an even more general fact of this kind, but I'll get to that. Now let me get to things that will look a little bit anomalous but are inherent in what I'm doing here.
Can I give you a new marker?
What?
Can I give you a new marker?
The marker. You want me to refresh it? I have a whole bunch of them here, so. Okay. So here's some things that I hope will surprise you. So I will have as another example, if I take something like M, okay, and I write, I don't know, okay, I'm going to have to, this is all hand wavy. I'll make it all precise in a minute. I'll write something plausible looking down. Here's, it's intended to be a natural number that's intended to be, let's say, a character string. Let's suppose we have these things. I'm going to claim that is in that, assuming I have such a thing. Okay? That's going to be important. In fact, I don't even have to go that far. I could even write here, I'll just write the word garbage. Okay? Oops. I'll just write the word garbage here. In other words, it's dead code. I don't give a damn what you write here. Okay? It will be the case that if, in fact, this is true, then this expression will be a natural number. And the reason is, if you run it, it runs by stepping to or simplifying to, by simplifying to 17, which I hope you could believe as I go along will turn out to be a natural number. Okay, so that's what I'm going to do. Here's an even more surprising one. An expression like this, if you, again, spare me a pinch of salt, I will get there. Okay, if I take an expression like this, okay, I'm going to claim that this is a type when M is a boolean. That this is a form of type expression. And in other words, it expresses a type. It's the exact same conditional, and it works the same way. And why is it a type? And essentially because any outcome for M induces a simplification to either nat, to a type, I'll say. And the type will be either nat or bool. So that's completely valid. I don't need any baloney about large limbs and some other dreary, horrible thing. I don't need universes, blah, blah, blah. It's a program. That's how you write a program. Okay? That's important. And now the last one that I'll write down for the time being is I will even be able to say things like what I sort of started out by writing. I got one step ahead of myself. I will even be able to say that this program, which dispatches on M and yields either a nat or a string, hand wavy, I'm going to claim that's a perfectly valid element of this type that says, well, it's either nat or it's string. Oh, to make it easier, since I'm only having nat and bool, let me write true here just to not introduce too many things. Okay, so if I do that, M. So I claim that this is also the case. If you know about formal type theory, everything on the board is nonsense. Okay, so those of you who don't know about formal type theory, just enjoy yourself, everything's good, okay? If you do know about formal type theory, you should be at least confused and doubting that I know what I'm talking about. Okay, so that's what's going on. So notice here, why should this fact turn out to be the case? Well, however M turns out, if M turns out to be true, and that's going to be part of the whole definition methodology, but I'll get to that. If M turns out to be true, then the answer is 17, which is a nat because it's the same M, which is why I needed deterministic operational semantics. Evaluating M had better give me the same value always. Okay, if it's non-deterministic and it can have various values, then this statement can't be made. Okay, so that's a hint that non-determinism isn't like somehow going to fall into this for free. Okay, but point is, evaluate M at 17, then in case it's a nat, it's true. If it's false, then that's a bool and we're good. It's a very kind of freewheeling, happy kind of thing in which specifications are programs. That is, types are programs. Okay, good. So that's the first important thing. They are programs. That's what they are by nature. That's how we start out, because there's nothing else. The claim is there's nothing else. That's all there is. And that's kind of, I don't know, to me it's kind of fun. All right, so that's a little bit of a preview. But I'm also going to talk, let me, again, at the level of a preview, I'm also going to talk about a key idea that I'm going to talk about in this work, and what are called families of types. And that's important. And in fact, I should write here type indexed families of types. So it gets to be a mouthful. Type indexed families of types. Okay, so that's what we're going to be looking at, which are sometimes called, I don't know, sometimes they're called dependent types. I guess it's okay, it's a fine word. I'm not sure who introduced that terminology, possibly de Bruijn. I'm not positive, some of you might know. Anyway, so this is the notion of dependent types. So an example of this is I might want to have something like maybe the sequences of a length n. So where we have here, I want this to be a type when n is a natural number. Or even more generally, I want to say that seq is going to inhabit something that will look like this. There's going to be, well, here's the terminology I'm going to use. A way of writing that out is I'm going to say if n is a nat, and then I use this double greater than sign. I absolutely, positively mean what I'm doing. I do not want to write a turnstile. It's not the same thing. Okay, so again, if you think you know formal type theory, then I'm already like, I'm off in the weeds from your point of view. Okay, so, all right, so n is a nat, we'll be able to write this seq as a type. Okay, and as a matter of fact, if I wanted to, I might be able to define sequence as, let me think about this for a moment. Okay, let's, can I think about this for a moment? Having a brain cloud, I know there's something I wanted to write. It'll come to me in a minute. Okay, so we'll do this. So you can understand that. So the point is that it's a family of types. A family of types that is indexed by a type. That's a central idea. And I want to get to that very quickly. So this is, I mean, for any fixed n, it's a particular type. But more generally, we can allow n to vary. And I'm going to have to explain the meaning of this, okay? And this is what is called the hypothetical, or Martin Luft likes to call it the hypothetico-general judgment. I'll just call it the hypothetical judgment. Or it can also be called the general judgment, because entailment and generality are kind of the same thing. So the general judgment. Okay, oops, I don't know what, I never know. There's a difference between British and American spelling, and I never know which is which and which one to use. Okay, so good. So hypothetical or general judgment, I want to talk about that. Okay, yeah, sorry.
Do you mean to write seq n after the...
Oh yeah, that's, well, yes. It depends on how you want to think about this. I could write a, if you want to do this. All right, let's do that. If I were assuming this were some primitive, that's what I would need to do. The brain cloud is I wanted to write a piece of code here, and then I forgot what I wanted to do. So I'll look at my notes maybe. Okay, so let's go on. Okay, so that's what I mean by that, okay? And then we're going to be able to have particular sequences, okay? Yeah, oh, hi.
I'm sorry, I do not understand the family of types and what sequence of n is that. Can you please
What was it?
Family of types and what sequence of n is, she doesn't understand.
What n is?
Sequence of n and family of types.
Oh, I'm going to get the, I'm about to define it, but I'm trying to give you, I'll get there, okay. I'm just suggesting there's going to be this idea which is called the type index family of types. So the idea is that you can, I have to broach an important subject, that's why I'm read this as saying, for every natural number, there is a type called sec of n, which is a type, and it's indexed by n, it's got an n in it. So if n were 0, it would be the type of sequences of length 0. That's my intuition, okay? Well, maybe I didn't say that. So I'm thinking of sequences of natural numbers, let's say, of length n, okay? So I was about to write. So for example, if I don't know what my notation for sequences might be, but you can imagine modulo getting, the specifics down, that this might be a sequence of length n. Okay, that's important, whatever n minus 1 is. So if we want to be more specific, let me write 9 here, and then this would be a sequence of length 10. Okay? And so that is a critical idea. A related critical idea, which I'm going to explain in a moment, is I might talk about a function which wants to have a type that looks something like this, okay? It wants to take in a natural number, and it wants to spit out a sequence of that length. And the problem is, how do I express that? Okay, well, the problem is I need to know what natural number you give it to tell you what the length of the sequence is that it emits. So the way you do this is you just give that a name, and then you write it here. You write it across the arrow, and that's the notation. Okay, I find that notation extremely natural, but in the literature, people always insist on using pi. Okay, you can do that. There's nothing wrong with that. But this is, I think this is a pretty nice notation. This is the new Perl notation. Okay, so that's an example of the kind of thing I'm heading for. Now, the thing that I want to account for here, which is important, is the following thing, which is the notion of functionality. It's not, what I said is not, it's not completely true. What is the issue is, what is the meaning of this? Okay, and the critical idea, let me figure out now, I have to obscure the thing I just wrote. I don't have much choice, really. Or I can go over here, maybe. Let's try that. All right. So the critical idea is what is called functionality. And why I'm not using turnstile. Okay, but it's important. The idea of functionality. The idea is that families of all kinds, we're also going to have families of types, and we're going to mention, I'll mention in a moment of elements of types. I'll show you about that. Okay, that these families must respect equality of indices, which immediately brings us into the question of what is equality. And what pervades my entire lecture plan is a question and answer to the question and the answer to the question, what is equality? And if you've studied formal type theory, you could understandably be confused. I'm going to explain a lot of things, I hope. That's my intention. So the central point is equality of indices. So, for example, this is a very evident one. You would almost not even think about it. A sequence of length 2 plus 2 ought to be the same as, what does that mean? I have to say what that means, a sequence of length 4. You wouldn't object to that. That's, you would think, oh, of course, it has to be. Or if I wrote something like, 17 else 18 on some boolean m, and I make a conditional decision, we should expect that, or in fact, if I specify this. There's lots of things I can write here. Well, let me write, I just thought of one that I could write, which should be the same as, in some appropriate sense, as if I do a sequence of 17, sequence of 18, dispatching on M. Okay, whatever I mean by same as, that should be the same as that. And in fact, I can then change to example I just inconveniently erased, and if I have here a type, oh, it wouldn't belong here. Never mind, I'll leave that alone. That's what I want to say. I'll get to something else in a minute. Oh, right. So my point is that these are types. These will turn out to be things I can validly say are types, and I'm dispatching on a boolean in order to emit a type. So this kind of a statement to say that it's same as in a typical formal type theory, you can't even say it. Okay, it's like you have a problem, okay, already. Or you have to get involved in much more complicated things. It's not a very direct thing, okay? So, all right, so that's what that's the critical thing. Oh, and now what I want to say is the following idea, and then I will start developing in more detail. So when I look at, let's say, so this is an example. This guy, so this guy here can be thought of as a family of numbers actually indexed by a boolean. And which number it is depends on which boolean you get. And this is a family of types indexed by a boolean, and which type you get depends on that boolean. Okay, so that's the idea. So this guy right here is a family of types, and so is this. Okay, in other words, if I write over here, well, this is an element. What am I doing? No, this is a family of types. I'm sorry. So if I want to write it out using some other notation, then I can write this out by saying, well, assuming A is a boolean, I'll use that letter for lowercase letters for variables. Then we will end up saying that this is a type. And in fact, we're going to end up saying it's the same type as this guy. So here I'm emphasizing, I didn't just pick an A out of the air. A specific A is quite generic in A. In other words, the statement that these are the same type, okay, so these are the same type. The statement is generic in A here. That's the thing I want to make, and I'm going to explain what I mean by that. Now, depending on what your index type is, the force of respecting equality, okay, which is what comes up here, that is 2 plus 2 being the same as 4, seems so obvious it's not worth saying. But as your type structure gets richer, when two things are equal is a property of the type that they inhabit, and it can be arbitrarily complicated. So an important theme that's going to be suffusing these lectures is the situation about what is true has a much higher, in fact, unbounded quantifier complexity, whereas the question of what is formally written down in any formalism is always relentlessly, recursively enumerable, which means that the things you write down in a formalism can never come anywhere near what is true. That's Gödel's theorem. Okay, so it's a use of these ideas.
I could just use those whole two sentences, like again, like hearing those two sentences again.
The ones I just said?
Yeah.
Okay. All right. Okay. First, I'll come back to them as soon as I develop the next things I want to do. Okay, I will. I'll say them again. Okay. I want to keep what's suffusing the lectures is a distinction between proof and truth. The other thing that's going on here that's going to come up is what do we mean by the same element, what do we mean by, in particular, the same type? The entire business of higher dimensional type theory arises from investigating when are two types the same. That's it, okay? That's what I'm going to end up with, at least that's my hope. That's my plan where I'm heading with this, with these lectures. Okay, so I've given you a bunch, let me just double check my notes. So I've given you a bunch of, right. Oh, I see, so what I in fact wrote down doesn't make sense. Okay, that's why I had a brain cloud. Something said to me, don't do that, don't do that. And I looked, and sure enough, I wrote a wrong thing in my notes. Okay, so at least I caught it. Okay, good. So let me look at this. Good. Oh, okay, right. Okay, give me a moment. Okay, good. All right. Okay, good. All right. Okay, so that's like a lay of the land, what we're going to do. So now let's talk about, oh, okay, right, no, I need a notation. So the notation I need now is, I erased it before, so I have to put it here. So now what we're going to do is we're going to revise our principal forms of judgment. We're going to take what we had before, we wrote A as a type, that's going to be generalized to saying what is called, I write it with a dot, okay? The reason is the equal sign gets overused, and when discussing it in the way I plan to discuss it, it's all sorts of possibilities for confusion. So I'm going to use a special weird notation, this equal dot. It's sort of a punctilious notion of equality. So that's why I call it exact equality, and that's why I write it with a dot. Okay. All right. So this is the notion of exact equality, and what I talked about meeting a specification or being an element is going to turn into, when do two programs equally satisfy the same specification? Okay? So this is also exact equality. This is exact equality. Oh, I don't know what I wrote there. This was supposed to be exact equality. I had some brain cloud there. I don't know what's happening. Okay, and this would be then, in that case, of types. And by the way, that'll be a somewhat dubious notion, and that's the whole idea of higher dimensionality, so I'll get to that later. Okay, and this is exact equality of elements. This is not a dubious notion, or members, and that's very fundamental, okay? So what I've used as my motivation for this is I need to be able to have it come out to be that these, by same as, I need for these to come out to be the same type. And I need for these to come out to be the same type. That's what I was motivating. And in particular, when I have a family like this, as I'm going to explain shortly, I need to know that if I plug in equal things, equal indices, I get equal results. So since 2 plus 2 is equal to 4 as natural numbers, then I want the results to be equal, okay? I want them to be equal types because the indices are equal as elements of the natural numbers. In other words, the family of types respects or preserves equality of indices. That's where equality comes in, okay? So this is the general thing. So this might be called equi-satisfaction if you want. It's a bit of a big mouthful word, but the idea is if we start with this meaning satisfaction, M satisfies the specification A, then the slightly more general form here says two things, M and M prime, equally satisfy the specification A. That's the meaning of it. And the critical point, which will come up again and again, is that when things equally satisfy specification or equal as types, but let's look at this line, it depends completely on A. Okay? That is what's going to happen. It depends entirely on what A is, okay? Depending on what A is, it matters a lot. So an example here, which you will know very well, it's going to be the case, so it would not be true, you would expect, that 2 would be equal to 4 when viewed as elements of the natural numbers, okay? However, you would expect it to be the case that 2 is equal to 4 when viewed in nat mod 2 nat. I'll just write nat mod 2, or the evens, the even numbers. It's not intrinsic. You can't tell by looking at it, okay? And therefore, 2 plus 2, or whatever, whatever formula I want to write here. Oh, what did I do? Yeah, no, I said that right, yes. And this I did not. Yeah, okay, I think I said what I meant to say. Okay, so the point is you can't tell by looking at the number whether the things are equal or not. It depends on their type. And yet, when you look in formal type theory, how equality is axiomatized as type independent. How can that possibly make sense? Okay? That's what I'm going to get to, okay? If you know about that and you don't understand that remark, fine, we'll get to it. I think you were first, didn't you?
So M prime inhabits A is a judgment,
Yeah.
right? M is exactly equal to M prime is also a judgment.
Yes.
But what we're saying is M is exactly equal to M prime is only a judgment in type A.
Well, no, M equals M prime in A is the judgment. It's three place.
It's like a three-part.
It's a three-part thing.
Okay.
M is equal to M prime when viewed as an element of type A. So 2 wouldn't be equal to 4 when viewed as elements of nat, but 2 would be equal to 4 when viewed as elements of evens, mod 2, if you're taking out by mod 2. They're both 0, in fact, okay?
Is it correct to think of exact equality of elements as a generalization of the exact equality of types to a set of things?
I don't know if it's a generalization, but it's certainly, they're totally analogous to one another. Yeah, exactly, yep. One is for types and one is for the elements of a type. Yep.
The first example there is the exact equality of types.
This is exact equality of types, this is exact equality of types, but it's derived from an exact equality of elements.
Yes.
Okay, that's the idea. Okay, so it's preserved, thank you, yes, that's correct. Okay, so good. So what we're going to do is this. So that's the general setup. And now I'm going to explain, oh yeah, I'm sorry, where did that go? Yeah.
This is just a syntactic question.
Yeah.
When you write M equals dot M prime and A, if you added parentheses around the M and M prime, would that then read that exact equality is in type A?
The question is whether it's equality in type A.
Parentheses around M equal dot M prime.
I don't want any parens, it's a three-place relation. If you want, you could write it like this. I guess that's okay, but anyway, it's not the way I'm going to do it.
Sorry, your question. I was just trying to visually disambiguate that from the statement.
See,
The exact equality is in type A.
this is expressing exact equality as elements of type A. Yeah. So, for example, yeah. So another example that might appeal to you, I don't know, is what's the one I usually use here? I can't think of my example at the moment. Okay, so I'll get there. I'll think of one in a minute. Okay, so the point is that I'm generalizing the judgment that M satisfies the specification of A to the judgment M and M prime equi-satisfy or equally satisfying the specification given by A. That's the meaning of it. And okay, so that's what's important. And then it should be the case. Okay, so the intention. This is what we're going to work out. The intention is that if we have an equi-satisfaction at A, and we also deem that A and A prime are exactly equal as types, then they equi-satisfy also at A prime. So we're going to define the semantics in such a way that this will always work out to be a fact. Okay? So I read it right now that the intention is that, because I'm now going to do my next layer of deepening. And so right now I'm stated as an intention. So the intention is going to be that if they're classified as being equally satisfying the specification given by A, and you deem that A and A prime are the same specification, then of course they should equally satisfy the same specification. So that's a kind of respect, okay, that goes on here. Okay, so that's the general framework we're going to be operating in for a little while. A little bit later in the week, I'm going to generalize this even further. And what I'm going to do, just so you know, what's going to happen is I'm going to put in here a bunch of variables. I'll put on the side in brackets, let's say x1 through xn, to represent n-dimensional types that are given by coordinate axes x1 through xn. They're specified by coordinate axes in a certain way. And then the idea will be that these are equal n cubes, and these are equal n cubes in that n cube. So we're going to have the idea of a cube inside a cube. That's what is eventually going to happen. Okay, so this is why I'm doing this. So then the notation will be a little bit more elaborate. We'll have this additional specification of the dimensionality. And what I'm doing is I'm writing down a notation for a kind of presheaf, and that, if you know about that kind of thing, and that's what I'm going to, the way I'm going to be handling the higher dimensional structure. But we'll get back to that a little bit later. Okay, so that's the general setup. Okay, good. Are we okay? I don't want to lose you. I don't want you to sort of go asleep and say, oh, well, I don't get it, never mind. I hope to keep you engaged all week, because I'm pretty sure I've got everything. I'm pretty sure I've got a good staging of ideas. So you should, I'm hoping you'll understand everything as I go along.
Is everything you're going to be talking about published?
What's that?
Is everything you're going to be talking about already published? Or is it
Yeah, the higher dimensional aspects are in. I'll mention it. I'll mention it when I get there. Yes, everything is. Look at my webpage, and then there are background references which I've erased at the moment, but that I gave before. I'll put something on Slack. But if you look in on my webpage and then you look in the references in the webpage, then you'll see a whole bunch of stuff. So everything's explained there. Okay, so good. All right, so let me carry on. Okay, so now what I want to do is, that was sort of a big kind of overview, okay? So what I want to do now is to talk about the semantics of these judgments. So what is the meanings of these judgments? And these are sometimes called meaning explanations, if you've ever heard that. Well, otherwise known as semantics, okay? Okay, and it's computational semantics. I'm going to explain everything in terms of how you run programs. Okay, so that's what's going to be important. Okay, so now I'm going to do the following thing. So the way in which what I'm going to do now is explain, first I'm going to give a general framework for the explanations, then I'm going to instantiate it, and then that will be the end of this lecture. So that's what I'm hoping to do here. Okay, so the framework is this. I want to explain the meaning of the judgment A equals A prime. I want to say what that means. I want to say, what does this mean? And I'll show you what this means. What it means is that A evaluates to, I'm going to write A naught. So remember, the notation I introduced, this will always be a value. So I'm going to say A evaluates to some value, and for lack of imagination, I'll call it A naught. Okay, and you'll see why I'm doing that in a minute. And I will say that A prime evaluates to A naught prime. And then I will say, and now this is a little move that I have to make here, write a subscript 0 there, and this is the same. And this is going to mean A naught and A naught prime are, I will write it like this. I'll write it with a hyphen, are equal type values. Think of that as one word. Or these are called, Martin Luff calls them equal canonical types. That's his terminology. So, but if I just do it like this, they're equal type values, okay? So, for example, I'm going to write down then. So, for example, I can specify. So, by definition, I'm going to say, bool, that's just a form of expression, which is a value, is canonically equal to itself, which can be abbreviated as saying, bool is a canonical type, and I'll write type 0 here to indicate that it's a canonical type, or a type value. Whenever I say canonical type, you could just replace that by type value as a hyphenated, its own word. Okay, so this means, that's a value, this is a value. I get to specify that that's the case. Bool is a type 0, and I'm just going to specify that. Okay, so that's one of the things I'm going to do. Second thing is we define in a similar manner what it means for M and M prime to be an element of A. So the story is, what I'm doing is I'm reducing the general case where these could be computations. So this could be, if true, then nat else bool, and that will be equal to nat because both sides evaluate to nat, and nats are canonically equal. That is, nats are types. I could also write that down as a definition. Yeah.
Is this a conjunction or an implication here? The means if, are you saying if this, then that, or is it all of this is a conjunction?
I mean that whenever the judgment on the left is defined to mean A evaluates to A naught, A prime evaluates to A naught prime, and, those are all and, A naught are canonically equal. They're equal type values. So that's a big, because that's a big conjunction if you want. This is a and
There exists an A naught such that, or?
Yes, if you want to say this, there exists an A naught, which is a value. Okay, there exists here A naught prime, which is a value, and this is the case. Okay, so that's the setup. Good. And now this reminds me of what I have to write here, where I assume, and these are the famous presuppositions, where A is a type. And what does that mean? That means A actually evaluates to something, and that something is said, those are said to be equal to itself as a type value, with the 0 here. There needs to be some notation. This is the only thing I could come up with. If you want, I could write here val. Okay, it's just a little more verbose. Okay, so I've been using 0, however, so I'll stick with that. Yep.
How does number 1 work if A and A prime are functions?
Well, I'm just saying they're any programs whatsoever, and they have to evaluate to values. And those values must be something that I stipulate as being equal type values. That's the sub-0.
So if A is a function, it is already a value.
Function of what? That's the thing. What do you mean by a function?
Some lambda term?
Well, in the setups that I have in mind, no lambda term will turn out to be a type. No lambda will turn out to be a type. That's going to turn out to be true. There's nothing that says that can never be true. I'm just not going to do that. Okay. So at the moment, let's just say, so the examples I kind of gave before. Well, let me just scribble it here. So if I have something like nat, let's assume nat is a type. So if I have if nat bool, and just to be boring about it, I will say that these are equal types. Okay, that will be a correct judgment. Why? Because this evaluates to nat. Look at it. This evaluates to nat because it's already a value. And I'm going to specify nat as a type. That's just going to be one of my definitions. Okay, so that's what I'm going to do. So that's how that will work out. Okay, good. Let me take a drink. So now I want to continue with the meaning of the next one. Oh, yeah. Mm-hmm.
So in this expression, you said that net evaluates to net, so that's why this is true. But if evaluates to bool, then bool won't be equal to net, right? Then it will be, so we will have ff there. But how will you know in future that your expression will be true or false?
Well, yeah, I simply wrote down a convenient expression for me to write it at the board. So what I literally wrote is the case. I could literally write this, in which case I would put that. In general, then I have to say, what are some true equations? And for that, I need a hypothetical judgment, and I'll get to that momentarily. Okay, so that's what I'm going to do. Okay, so can I continue here? Okay, so if I already know that something is type, I can talk about what does it mean for these things. So what this does, what does this mean? It means that this evaluates to a value, and if you want to do that, M prime evaluates to a value, okay, for some M naught and M naught prime. And we specify, okay, that these are going to be equal in the type that we specify, which really means, let me expand that A evaluates to a value such that, well, that's what we have here. So we have that information up here. So I forgot that I wrote that here. So since I wrote that information here, then I'll just write it like this, that these are equal canonical elements of the canonical type. So these are equal values in a type value. Okay, that's the important thing. That is the general kind of setup. And then what I'm going to do, and I'll do now, I will instantiate that to a particular case so that you can see what's going on. I need one more idea, though, which I broached, which are really two, another pair of ideas. So let's write this up. Okay, so now the next thing I need to do is tell you what does it mean to talk about, let's call this B equals B prime. And what does this mean? Well, there's a concise way to write it out. And what it says is this, is you say, this is the notion of functionality. If M and M prime are equal things in A, and B with M for A is equal to B prime with M prime for A as types. And this is this notion of functionality. If you want to work out some special cases, treat this as B type. If this is B type, then I'm just saying B respects equality in that position, because B type means it's equal to itself. And so then this will be the same thing. I'll leave the B prime here. So what you can do is check for yourself, do the various special cases. So it implies, so there are various things that it implies. So check, I will ask as an exercise, that if you have A and B as a type, means, because this by definition means B is exactly equal to itself. The setup. So we say that this means that if M is equal to M prime in A, implies that B respects that. We get the same type back. So this is the 2 plus 2 equals 4 in NAT, then sequence of length 2 plus 2 is equal to sequence of length 4. That's the idea that I gave a moment ago. That's a special case. And it also implies, if I give you the exact same element on both sides, if M is an element of A, then I will get B of M is equal to B prime of M. So you get all the combinations of M and M prime. That's the idea that's going on. And the last thing, and then I will make this concrete, and I hope that that will help and that will finish us for today. Okay, so what I will do here, and what does this mean? Well, it means if I plug in equal things, oops, that should be a prime. If I plug in equal things, I should get equal results. So it means that if we give me equal things, then I will get back in B, let's write M for A. And notice where I should really write this over here. So assuming that, and in order to even write it down, that the classifier is actually a type. So B is equal to B, which is the same as saying B is a type, a family of types indexed by A. So assuming that the type makes sense, that it is a type indexed by the elements of A, we assume that, because then what this statement means is, here's an arbitrary choice, but that's the same as writing B of M prime for A, because our presupposition is that B is functional in the variable A. Okay, so that's what's going on. So therefore, if I have the assumption on the left, this will be equal to that. Therefore, because they classify the same things, it doesn't matter whether I have B of M here or B of M prime here, they're the same. And then these two guys are going to be the same as each other. Okay, that's the setup. Good. All right, am I losing you? Are you falling asleep? Okay. All right. I can't have the conversation with you I want to have until I get like these basic things on the table. Okay, so that's very, very important. Okay, good. All right, so that's the general setup. So now let's look at some specific instance of it. And then we'll see how this works. I hope I'll get 2 examples in. Let's see how this goes. Okay. So let me do the first example. So now let's be more precise about the things that I was waving my hands about earlier. Okay, so first of all, let's talk about the booleans. Okay, so the first thing I'm going to say, I'm going to say, first of all, 1. Bool is equal canonical or equal type values to bool, which is a way of saying bool is a canonical type or a type value. That's the sub-zero notation that I'm using. Okay? So what I'm saying here is, i.e., I'm defining that this expression, particular program, which happens to be a value, I'm saying bool is a type. That's the idea. So there's sort of 2 aspects of this. One is I'm saying a certain program is going to be the name of a type. That's what is going on here. So if you want to think of it, you could also say, there are different words one can use. You could also say it names a type. Because which type it names is determined by what I'm going to write next. So first of all, what I'm saying is, here's a program, bool, and bool is something that I'm going to be considering to be a canonical type or a type value. As it happens, I am not going to say, just so that you can get your bearings, I am not going to say, although there's no reason why I can't, but I'm not going to say that 17 is a type. It's a value, but I'm just simply not going to define that particular program to be the name of a type. I'm just not going to do it. It's not like I can't. It's not like it could never be. It's just, as a matter of fact, I'm not. Okay? So as a matter of fact, I'm saying that bool is a program that names a type. It's a particular value, and I'm going to consider it to name a type. And then the question is, what type does it name? Okay? So I can write this in one of 2 ways, but I want to do it like this. What I will say is, I'm going to say that the membership relation, m equals m prime in bool, there's different ways to say this, canonical elements. So let's write these canonical elements. Because, you see, the apparatus on the previous slides, these 2 things that I've written down here, that's generic terminology or notation that I'm going to use in the process of making these other definitions. Here, it will not, with bool, it's so elementary, it will not come into play some of the more subtle aspects of it. That'll come up in a moment. But I'm just going to say here, when is this the case? Okay? So I want to say, there's various ways I can say this, but what I want to say is that it's the strongest relation, and sometimes people will say least, or I don't know, other words like that. You have to have an extremal quality to the word you're using. It has to, because I'm giving it by a universal condition, what's called. So it's the strongest relation, relation. If you really want to be very careful, like I say, it's the strongest relation R such that the following 2 things hold. But let me just write it like this. Such that I'm going to claim that true is, guess what? You're not going to be surprised by this. That true is equal to true, which is the way in which we say true is a canonical value of the canonical type bool, or the type value bool. Okay, so I can do that. And false is equal to false. In other words, I'm saying false is a Boolean. And that's my definition. So here it is kind of helpful to think of this. Bool is going to be something that I use to name types. What does it mean to name types? It means that they index an equality relation. That given bool, the relation blank equals canonical blank in bool, for fixed bool, I have a binary relation here. So another way to write this out is it's the strongest relation R, such that R relates true to true and R relates false to false. That's maybe the most really precise way to write it down. Okay? So that's the way in which I'm writing it out. So if you want, it doesn't look too nice to do this, but I could kind of put parentheses here, because what I'm doing is I'm fixing bool and I'm saying epsilon bool. As elements of bool, the binary relation blank equals blank as elements of bool is given as the strongest relation, such that true is related to true and false is related to false, and that's it. Okay? So implicit here is the extremal clause. So the idea, if you're not familiar with this, is we should point out that what it means, part A, is the stated facts are true. The stated conditions are true. In other words, true is actually in there. I'm writing this out for people who maybe are not so familiar with this kind of terminology. And it means that nothing else is true about that relation. And nothing else. So the strongest, saying strongest here, or least, or words like that, is I'm saying true is equal to true, false is equal to false, and that's it. Nothing else is the case. So in particular, I know from this that true is not equal to false. Okay, that's important. By definition, because I'm defining it in this universal way to be the strongest thing of this sort. Yes?
Is it fair to say that you're defining a relation on bool before defining bool?
I wouldn't call it a relation on bool. I'm just saying there's a relation called blank, oh, I erased it. Blank equals blank in bool, mix-fix syntax. There's a relation which...
So what kind of relation? Binary relation?
A binary relation, yeah. On programs.
Okay.
That's the idea. Well, actually, when I define it with sub-zero, I'm defining it on values. And then it's extended to not values by the way I described in the previous. Okay, that's the idea. So, yeah, so if you like, I can say what I'm doing is, as I mentioned, it's the strongest R, strongest binary relation R, if you want to write it like this, between two expressions, if you want, such that it relates true to true and it relates false to false. Now, here is a crucial idea. I am expecting you, so you must, in the sense that you must accept, I will say, this as a valid definition. Now, what do you mean by must? What I mean is, the formulation I'm giving you, for reasons that I can elaborate, I don't believe that there is any better way to proceed than the way in which I'm proceeding. You could doubt that I've defined a relation. Here it's so simple you can't possibly doubt, but if you can just, think about it for a minute. If I say to you, oh, I want the strongest relation R such as something or other, you should be saying to yourself, well, why does it exist? Because when I say the X such that P, well, who knows? I mean, it might be complete garbage, okay? So I have to say that. I'm asking you I'm basically saying you have to accept this. And the reason is, it's a principle of Gödel's theorem. Whatever rules you write down as being admissible definitions, in order to justify them, you're going to need ideas that are even stronger than what I'm asking you to accept. There is no way. The whole point about Gödel's theorem is there's no way to win the game of specifying truth, of saying what truth is. That is, whenever I tell you what I mean by things being true, like what is the relation of equality, the judgment of equality in the type Boolean, I'm specifying what that is, the strongest relation like that. You could try to talk around what that means by having a theory of relations and specifying what that theory of relations is, but then I have to ask you, well, but then what does that theory of relations mean? And it's only going to be more dubious. That's the whole point of Gödel's theorem, is whatever you do, it's going to be even more dubious. There's no way to get rid of the dubiety. That's it. It's impossible. So what I'm asking you to accept here, and that's what must means, I'm asking you to accept here, is that the definitions I'm going to give you define something, that this is meaningful to you. I claim there's no other way. Now, in the papers that I mentioned that you can find on my webpage, we actually do outline another way. For social reasons, we want to relate to a community that's not familiar with these ideas. So that's the thing we do, okay? However, we can talk about it offline. For fundamental Gödelian reasons, you just have to stop. You just have to say that's a valid definition. There's no way to get around that, okay? That's very important, I think. Okay, good. So now I want to say, what does it mean to be the strongest relation? I want to use that fact. I have 3 minutes. Okay, so I guess I'm going to have to pick this up. All right, well, let me let me get to the following thing. Okay, now I'm going to say something I alluded to earlier. So I'm going to say, I'll write it, I don't know, proposition, fact, assertion, claim. Okay, and I'll sketch a proof for you. The claim is the following thing. If you have a boolean and you have a type and you have M1 is in that type, and M2 is in that type, then, so I have if then, if this, then we have the following thing. If M1, M2 of M is in A. This is, I can say more important things than just this, but I can say this. And let's look at how we prove it, okay, in the couple of minutes I have remaining. Okay, I'm supposed to be 1 hour and 20, right? That's the idea? Yep, okay. Okay, good. So here's the thing. So we understand what is being stated here. So if you give me a type, and you give me a boolean, and you give me 2 elements of that type, then it's a fact that the conditional inhabits that type. It's not a definition. So that's what's important. In a formal type theory, this would be like one of the rules, and it's just a definition. Okay? I'm actually going to be able to say something even more interesting shortly, but I won't get to it in this lecture. So I want to claim this is basically a theorem. So how do we prove this? So we're going to prove it. How do we go about proving it? And the key is that bool, the epsilon bool, is given by a universal property. Namely, it's the least thing, I'll say it's the least containing, it's least containing true and false. I'm specializing this down to just an element at a time. Or really, let me just do this. It's the least thing. Okay? What does it mean to be the least thing? Okay, so the idea is, what I do is I fix my A. We've got that done. And now what I'm going to do is I'm going to consider the property, I'll look at it like this, P of blank to be, I can even fix, not only can I fix A, let me think about this for a moment, not only do I fix A, but I can also fix M1 and M2. In some other situations I can't. And now what I want to prove is the following thing. So what it reduces me to is what I'm saying is I'm proving a property that says if M is in bool, then some property with an M in it. Namely, that for those fixed things, in other words, if we fix this in advance, if M1, M2, M, I claim is in A. So I have if M is in bool, then something involving M is in A. Once I fix my A and my M1 and M2. So this is what I need to do. Okay, now I use the universal property. It's sufficient to show because for M being in bool, what it means for M to be in bool, let's check, okay? For M to be in bool means that M evaluates to M0, and M0 is either equal to true or it's equal to false. Because that's the definition. Because the definition is M0 has to be a canonical element, value element of bool. And the value elements of bool on the upper slide, where did it go? It's behind me somewhere. It's behind me. The value elements of bool are, by definition, either true or false. Okay? So the idea now is it's sufficient to show the two cases. I'm spelling this out in excruciating detail because I want to illustrate, I want to show you the skeleton, the bones of how all this works, so that when we get to more complicated things, it'll be more natural. So it suffices to show this is for true, and I want that to be an A, and this is for false, and I want that to be an A. Why is it sufficient? There's something really important. There's an important thing here why that suffices. It's not merely that bool is defined to be the strongest thing containing true and false, because those are the elements. It's important here because the if evaluates its principal argument. The reason is, so the idea is that if I want to go back to the M, the point is the evaluation rule I gave you in the beginning of the lecture tells us to evaluate this expression, I first evaluate M. That's important because then I can reduce it to this case. And for this case, if we do part A, then the conditional M1, true, that steps to M1, and we know M1 is an A. And B, the same thing is if M1, M2, and that's false, that steps to M2, and we have by our assumption that those are in A. So to finish, so I have this. So this steps to something which is in A, so I claim that it's actually in A. So I claim from there. So I rely on the following fact. A little generic lemma, which is always called head expansion for historical reasons. Or if you want to be obtuse, it could also be called reverse execution. So the kind of weird way to put it is, typing is closed under reverse execution. If I have an element of A and M steps to M prime, I run it backwards, so to speak, then M is an A. And I'll leave this as an exercise. Check this, okay? Prove it using the definitions I gave you in terms of evaluation to canonical form. So I'll just leave that as an exercise. Okay, we'll do that. And then here I'm done. Because now I have, if I want to show that this is equal to here, I have to look at how the evaluation goes. And the way the evaluation goes is this guy steps to either M1 is in true, that's one possibility, or it steps to this. Why? Because M does. M evaluates to, which means that it steps to M0, which is either true or false. So we have a whole bunch of transition steps here. We have a whole bunch of transition steps here. This guy takes the next step to M1, which is in A. So under reverse execution, this is in A. And under reverse execution, this is in A. And so I say here is M2 is in A, reverse executes to here, which reverse executes to here, so therefore that's also an A. And then I'm done. I realize that I'm rushing this because I'm at the very end of my lecture, okay, but let me just leave it at that, okay? And I can follow up with you separately if you need to, or I can put something on Slack or whatever, we can work that out, okay? So the key idea of the proof is head expansion. So this is the central idea, the main idea. So the main idea of the proof there are two things, okay? So what I'm doing is, one, I'm using the fact that bool is inductively defined. That's what I mean to be the least or the strongest or whatever. Bool is inductively defined. And typing is closed under head expansion. So if I want to show that the conditional in general is in a type, it's enough to show that the things it reduces to are a type, and then I pull that back along the execution step, the execution path. Again, determinacy is important here. Okay, so that brings me to the end. Yes, I'm over time. Okay, so that's enough for today. And what I'll do is I'll pick up on this tomorrow, looking at more type constructors, and then a more deeper investigation of what I mean by equality. So we'll get to that. It'll get more interesting now in terms of the content very soon. So what I would suggest to you is that it's really important to understand from today the overall architecture of the explanations, and to let us get down. I'll write it out on Slack for you. Get it down on paper, like make sure you understand how this argument goes, because I'm going to use this kind of argument again and again and again. Okay, so I'll show you. Okay, so that's enough for today. Thanks for your attention.